low temperatures with the BITZER two-stage compression technology. So at first here, we have a look at the different types of two-stage compressors that BITZER offers. Here on the upper left, we have the, sorry, flip that too quickly. Here on the upper left, we have a open drive type two-stage compressor. So you can couple a motor to this. We have a semi-hermetic in the upper right, and on the bottom, what you're looking at is a tandem version of the two-stage compressor, and you can see that there is an economizer. You'll see the black box on the front of the compressor on the right-hand side there. So these are quite a bit less common in North America, but these are another product that BITZER produces, and they all achieve the same goal. This is refrigeration generally that you can operate down to about minus 90 Fahrenheit saturated suction temperature. So here's the compressor that we're going to focus on here. Okay, so again, this is the two-stage compressor, which is basically a modified version of a single stage. In this particular case, it's a 6-cylinder compressor, just a little bit of external manifolding and a few things that make it a little bit different. And no, we do not offer retrofit kits to convert a single stage over to a two-stage. They're a little bit more involved than that. So what we're going to look at today are, well, we saw the compressor configurations, but we'll talk about the configurations of how you can incorporate the compressor into the circuit, application, theory of operation, overall system layouts. So we get into subcooling versus desuperheating modes, the interstage components that are required, two-stage compressors, because you have two stages that are essentially working in series. We need to have some auxiliary cooling injected into the process. Otherwise, the discharge temperatures just get super high, and we end up with a situation where we're burning up the very oil that we're trying to lubricate the compressor with. Just a few key notes on startup and commissioning. This isn't going to be an exhaustive talk on that. I'm just going to hit on some points that are specific, very important to the two-stage compressor. Capacity control. How do we control capacity with the two-stage compressor? And then we'll get into paralleling of the two-stage screw compressor. So at first, we'll say the single-stage compressors, the limiting factor in their use is the compression ratio. And the higher the compression ratio, the higher the discharge temperature, the more, we'll say, leakage and more re-expansion of gases, and that takes place. So the efficiency drops off, and to a point where you've got a fair amount of energy input into the compressor, but your output is very low. So very low efficiency. So the two-stage allows us to offset that substantially. Reliability also, when you're running very high compression ratios, places additional load on the bearings, creates lubrication challenges, as I mentioned before, high discharge temperatures leading to carbonization of the oil breakdown, what have you. So obviously we want to avoid these at all costs. So in these situations where compression ratio is going to be high, multi-stage will be used. Either, you can use separate compressors, you can use multi-stage systems such as, boosters and cascades and auto cascades and what have you. In this case, we're using an internally compounded compressor, one compressor that's been reconfigured for a two-stage setup. So if we look at a minus 40 Fahrenheit saturated suction temperature and 110 saturated discharge temperature, we can see where the operating point falls on the envelope here for a typical single stage compressor. And you'll note that in that gray, the darkish gray area there, the note at the bottom of the page indicates additional cooling and suction superheat below 35 degrees Rankine. So 35 degrees above your saturated suction temperature would be the absolute max. So, and you would need a head cooling fan for sure. And in some cases you need liquid injection and a head cooling fan. So these are to, of course, keep the compressor cool and to keep that oil from burning up on us. If we take these same conditions now and and just exchange the compressor for a two-stage compressor. This is what we're looking at now. So we have the envelope where basically I like to call the operating envelope the sandbox, also for the compressor. In this case, you can see where the blue X indicates the operating condition. And you can see we're well inside the envelope with no auxiliary, no head cooling fan required in this case. Although there's auxiliary cooling, interstage cooling, which we'll talk about. This is basically, you're basically at the top, getting close to the top end, if I can say that, for a two-stage compressor with lots of room to go in terms of saturated suction temperature. You can go down to, like I said, almost minus 90 Fahrenheit saturated suction temperature or so, depending on what your saturated discharge temperature is. Taking comparing the compression ratios would look something like this. If we have a system, and I'm not sure why I'm changing conditions here, but we're going to use a different example. Minus 50 Fahrenheit saturated suction temperature and 100 degree Fahrenheit saturated discharge temperature with a single stage compressor. And keep in mind that when you're calculating compression ratio, this has got to be done using absolute units. Okay, so if you're working with sea level atmospheric pressure, then you would take your pressure, your PSIG rating, and you would add 14.696 or 14.7. Okay, and so you would do that with the suction, you do that with the discharge, you divide the suction into the discharge. So in this case, we have 250 PSIA divided by 15 PSIA, resulting in an overall compression ratio for the single stage compressor of 16.67. The two-stage compressor, because we've got two stages to make up this overall compression process, now it looks something like this. We have the same high side pressure, of course, or discharge pressure at 250 PSIA, and we have the low side or suction pressure is 15 PSIA. And to calculate the approximate interstage for a 6-cylinder compressor, we would multiply the two absolute pressures, suction and discharge, together, take the square root of that number, and in this case, it works out to 61.2 PSIA. And this will get you, plus or minus 5% of the actual number that you'll find in the software. So if we were to break down each stage of the compressor, you can see the high stage now, we still have the same discharge pressure of 250 PSIA, but its suction pressure is essentially the interstage pressure, which is 61.2. So we divide the 61.2 into the 250 and we get a compression ratio of 4.08. In the low stage, it's similar. We have an interstage is actually the discharge for the low stage. 61.2 divided by 15 PSIA results in 4.08. And this is basically what we're trying to accomplish is equal compression ratios to optimize the performance in each stage as much as possible. So basically, you could say, even though the overall compression ratio, if you're reading suction and discharge, are quite high, the individual compression steps within a two-stage compressor, compression ratio is significantly lower. This results in much greater efficiencies, higher capacity, the whole bit. So if we take these operating conditions and place them into the BITZER software, minus 50 and 100 degrees, and it's R404 in this case, we can see that the software reports that the interstage pressure is 58.5 PSIA, and that works out to be only 2.5 PSI less than the calculation. So when I mentioned before that compression ratios, the higher they get, the more challenging it becomes, because then we run into situations where we've got the re-expansion of gases, which is the one thing I mentioned, where when you compress a refrigerant, okay, just imagine compressing that refrigerant and then the piston reaches the top, but it never goes all the way to the top. We need to leave a bit of space because we never want to get to a point where the top of the piston can come into contact with the valve plate and the suction reed valves and what have you. So there's always a bit of a gap. So with that high pressure trapped up there, okay, when the piston starts traveling downwards, that trapped refrigerant will re-expand. And the higher the difference, or the higher the compression ratio between the discharge and the suction, the more of that stroke is used up re-expanding that refrigerant. So you can essentially get to a point where those pistons are going up and down and just compressing refrigerant, and your overall throughput, which we call mass flow rate, is less. So let's talk about the theory of operation of the two-stage compressor. So we have a suction manifold. So for a 6-cylinder compressor, the top head and the right-hand side head, if you're looking at the oil pump end of the compressor, are coupled together via a suction manifold. Now, the suction manifold has a screen inside, a suction screen, basically a long cylindrical screen that actually sits inside that chamber. I'm just trying to figure out how to get my pointer working, but with my different setup today, I don't seem to have that. But anyways, I don't want to mess around with it, so we will just keep going. Okay, so you can see the suction manifold. So the evaporators are connected to the compressor, of course, via the suction line, and then at the compressor, then we split that off to 2 heads. So we essentially have 4 cylinders compressing the low pressure refrigerant from the evaporators. Next, we have the interstage mixing pipe. Okay, so this interstage mixing pipe is actually at interstage pressure. That's that 61 PSI or so in the case of a -50 and 100 system. And in this case, the refrigerant that leaves those 4 low stage cylinders now is sent to the back of the compressor where the motor barrel is, because this is a refrigerant cooled motor. So we need to have relatively cool refrigerant entering the motor. However, we just compressed it. So how cool could it possibly be? And this is where interstage cooling becomes important. We have to make sure that we have enough interstage cooling so that we don't overheat the refrigerant and the oil, but also we have enough cooling. So let's take a look at this using another approach. So we can see our suction line is split via the header, the suction manifold or header into the 2 groups of cylinders, 2 groups of 2. Okay, so we have our low pressure stage, and then on the discharge, they're paralleled, so they're coupled together, and then they travel through this interstage mixing pipe. But the next thing they have to do, we have to cool the motor at some point, but we need to also inject some form of auxiliary cooling. So this will be in the form of a refrigerant from the cycle that we're going to inject into the circuit. Okay, so here's our motor heat. So we pre-cool we cool the refrigerant after it leaves the low stage, and then we absorb motor heat, and then the refrigerant travels to the high stage, which is the final stage of compression, and then out and off to the condenser. So you may be wondering, well, why do we have more cylinders in the low stage versus the high? Well, it's very basic in principle. If you consider the specific volume of a refrigerant, and I just picked 2 arbitrary values here, -40 and +40. At -40, specific volume of the refrigerant is 2.13 cubic feet per pound, and it's the refrigerant takes up much less space at the higher SST because the pressure is higher. So as you're compressing the refrigerant, each pound takes up less space, so we require less displacement, less compressor displacement in the high stage to handle the overall mass flow. So suction gas comes in, splits off via that suction manifold into the 2 low stage heads and cylinders. And then these cylinders compress the low pressure refrigerant from the evaporator up to the interstage pressure. And then after it leaves these cylinders, or the valve plates of the low stage cylinders, the refrigerant enters this mixing pipe that you see here on the left. And then that travels back towards the motor. And you'll see that there's a note there. It says LI. That's basically a liquid injection valve. This is a simple way of applying auxiliary cooling to this compressor, but I'm going to be showing you both methods. I just want to show you the flow path inside the compressor for now. Okay, so this is basically the low stage compression process. Now we're going to continue from this mixing pipe. You can see the red arrows. We have fairly warm refrigerant leaving the low stage, and it travels through the mixing pipe all the way to the back of the motor barrel. And the injection valve, in this case, as I said, a liquid injection, this is the simplest way to achieve, this is the minimum requirement, is probably a better term for it. We need to, at the very least, have a liquid injection valve, but a better mode would be subcooling. Will get you higher efficiencies and capacities. But I'll explain the difference between the two and how we connect them. So with that injection there taking place, now we cool the refrigerant. So we do a little bit of pre-cooling before that refrigerant enters the motor, because we have to extract the heat from the motor to keep the motor happy. And then once the refrigerant passes through the motor, absorbing heat, then it's going to enter the high stage cylinders, the final two in this case, for compression up to the final discharge pressure, and then it'll be off to the condenser, usually via the an oil separator, being a very low temp system. Note also that the crankcase pressure in a two-stage compressor is at interstage pressure, not at suction pressure. Now, for those who use the suction line pressure as a reference for checking oil pressure, just to point out, that's the incorrect way of doing it. You should always check the pressures at the crankcase or at the pump inlet versus the pump discharge is the proper way of doing it. And the reason for this is, you have strainers. A suction strainer could have some debris in it, and even the suction strainer itself could produce a tiny bit of pressure drop, and you want to get a reading that's as accurate as possible. So you check it at the pump. Net oil pressure means pump inlet, pump outlet. So the final stage would be, again, the refrigerant, after it absorbed the heat from the motor, now it enters the final stage of compression and then off to the discharge. Inside the compressor, we have a partition that separates your motor compartment from the compressor or the crankcase compartment. And the crankcase, of course, is where your oil is. So they're separated. Suction gas comes in, as I mentioned, we cool the motor. And this is actually what I'm showing you is the view of a single stage. And this isn't meant to be confusing or anything like that, but the idea is really just to show the partition and the vent valve. Just the only difference here is this slide really should be modified to show that this is the interstage mixing pipe coming in. So let's call this interstage flow, okay, from your low stage cylinders, comes in, absorbs the heat from the motor, and then into the high stage cylinder. But similar to the single stage compressors, we use these crankcase vent valves on the partition, and also there is an ejector at the bottom of the compressor in the crankcase to return any oil that is entrained in the refrigerant that comes back from the suction line, drops out of suspension, ends up in the bottom of the motor barrel, and then the ejector can bring that back into the crankcase. And by having the vent valves there, really suppresses foaming in the event that there's a fair amount of refrigerant in the crankcase oil for whatever reason, and it starts to foam up rapidly on startup, then that would be a problem. And the vent valves restrict the flow. So when the compressor starts up, the refrigerant slowly vents out of the oil or the crankcase area over to the motor barrel to suppress foaming. That's one of its main features there, purposes. Okay, so there's a sealed main bearing here, and then we have the ejector oil system. This is no different than what's done in the single stage compressors. Okay, so another way to compare the single stage and the two stage. This is very interesting. This will show you the difference in performance for a compressor that is a single stage versus a two stage, but with the exact same displacement. So a 4,710 cubic foot per hour compressor in a single stage, and I should really update this slide actually, because this is the previous version of the compressor. We called it .2 generation, and this compressor now would be an Ecoline, which would be a 6HE version. And in this case, we have 4,710 cubic feet per hour, and we're operating 404 at -40 and 100 degree, so minus 40 saturated suction temperature, 100 degree Fahrenheit saturated discharge temp. And then we've got no subcooling in this case, just for an example, and a 65 degree return gas. So displacements, when you add up the two stages of the S6H-20.2 two-stage compressor, they add up to 4,710. So we're comparing like for like displacements here. The coefficient of performance for the single stage is 3.98. The coefficient of performance for the two stage, it goes up, a bit to 4.45, which is a 12% increase, which is nice. It's always nice to see higher efficiency numbers. Doesn't tell the whole story, but that's part of it. Capacity is 52.4 of the single stage, and then the two stage is 74.5 thousand BTUs per hour. Okay, and in this case, your increase there in capacity is 42%. So 12% higher efficiency, but you're getting a lot more capacity. So that's another part of the story there. Then we have the compression ratio of a single stage would be 13.85, whereas each stage in the two stage operate at 3.72, 3.73. Nice and low. Lower compression ratio always results in a higher flow rate through those cylinders and higher efficiency, more bang for the buck, basically. Power in kilowatts for the single stage is 13.8. And then when we go to the two stage, it's 16.75. So it's just, again, we don't get something for nothing. So the power increase is 27%. However, there's a big difference in capacity. If your load is only 52,000 BTUs or so, we don't really need a 74.5 thousand BTU compressor anyways, right? So in this case, we can kind of go back to the software and select a compressor that's closer to the 52.4. And you'll see that you're definitely going to be dropping the compressor size. And then a decision's got to be made as to whether 46,000 is going to work or 65.3 thousand BTUs is going to work. But either way, now your power consumption is going to go down even further. Your efficiency numbers are greater. So these are the main benefits of applying a two-stage compressor. So let's take a look at some system design of the two-stage. Okay, so here's the most common way to apply a two-stage compressor in, say, a condensing unit. We have the interstage, which I mentioned before, and the main components needed in a subcooling type approach. So we're basically what we're going to do is we have interstage cooling. That's a requirement, no matter what, with a two-stage compressor. But since we have access to an interstage, this gives us the ability to set up another evaporator, if you will, and use that evaporator to cool the refrigerant that leaves the receiver and travels towards the expansion valve on the main low temp evaporator. Okay, so we have a braze plate heat exchanger, you can see here in the circle, and then we have an expansion valve. And also BITZER provides the interstage kit, which includes the filter, the solenoid valve, and the sight glass. Okay, and then with the expansion valve, there's an orifice depending on the application, depending on the size of the compressor, and then we select the orifice, and then that's included with the valve and with the compressor. So refrigerant circulating in the low stage carries heat that's, of course, absorbed in the evaporator, any heat that's picked up from the suction line, and any heat during the compression process in the low stage. So this will be your heat of compression, which every compressor has. Refrigerant circulating in the high stage, on the other hand, carries the heat from the discharge gas leaving the low stage, okay? Because these two internal compressors, we'll say, are in series. So everything that leaves the low stage now ends up in the suction of the high stage circuit. Okay, so the high stage has to carry all of the refrigerant that left the low stage, all of the heat that's absorbed from the main liquid line during subcooling, and I'll show you how this works. And also, it's the interstage is where the motor is located. So the interstage is, the high stage is also going to be carrying that flow. Ultimately, the high stage carries all of the flow. Okay, so what we'll do is we'll follow the flow. We'll follow the refrigerant through a circuit. So we start out with this purple line here, which is your high stage. Refrigerant leaves the discharge, travels into an oil separator. Generally, you're going to have an oil separator in low temp systems like this because oil travel becomes very complicated when you get into lower temperatures. So you want to generally use a good quality, high efficiency oil separator to limit the amount of oil travel out into your refrigeration circuit. Refrigerant then travels to the condenser where we desuperheat, condense, and then subcool. And from this point, now we have subcooled refrigerant ends up in the receiver, just a buffer tank, if you will, storage, where that liquid level is going to float throughout the year, depending on load, depending on ambient temperature, depending on several things. And the idea is just to always have enough liquid in that receiver. But instead of just having that liquid travel to the evaporator now, in this case, what we're going to do is we're going to split off our liquid line. So the blue line that comes off to the left, just after the sight glass, goes into the brazed plate heat exchanger, out of the heat exchanger, and towards the expansion valve. So the purpose of that heat exchanger, which is a brazed plate heat exchanger, is to subcool that liquid. So we're going to refrigerate that liquid. And when we refrigerate the liquid, we've increased the heat capacity of the refrigerant. So if you take an extra 10 BTUs out of a pound of refrigerant, for example, before it enters the expansion valve, that's an additional 10, I don't know if I said 10 pounds, it's 10 BTUs anyway. So if we take out 10 additional BTUs, then in the evaporator, that same pound can absorb an additional 10 BTUs. And that's for a given compressor, a given displacement. Okay, so we're subcooling the refrigerant, and then that's our main liquid line, is what you see in blue. Okay, up to the expansion valve, and then through the evaporator, where after the refrigerant's expanded, we absorb the heat, and then we superheat to protect the compressor. You're generally going to have an accumulator on a compressor. Keep in mind, these are direct suction compressors, so you want to make sure you've got good, stable, sufficient superheat, and also a good idea to have a trap for those transients where you may have a little bit of liquid traveling down that pipe. And in a well set up system with proper defrost and everything else, you should never see this, but sometimes this will be the case. Then the suction gas travels back to the two heads that I mentioned through that suction manifold on the compressor. And then we start the process all over again. So going back to the receiver outlet on the far right of this drawing, you can see where that line split off. So we followed the blue line, which is your liquid, okay, traveling to the main evaporator. We're refrigerating that. But in order to accomplish this, we need to take some of the refrigerant from the liquid line, which is generally going to be piped off the bottom of the liquid line. So we have a good quality liquid there. Keep in mind, this is auxiliary cooling for the compressor as well. It's not just, first and foremost, it's about interstage cooling. But secondly, as a nice side benefit, we're subcooling to improve capacity and efficiency as well. So some of that refrigerant travels through another expansion valve, and we'll call this the liquid line accessory kit on the lower right, where it says expansion valve. And this travels through the cold side of the brazed plate heat exchanger, and we're going to evaporate refrigerant to accomplish the subcooling. And then the cool refrigerant that leaves that heat exchanger then enters the interstage mixing pipe. Okay, you can see where that green line enters the mixing pipe, and that's what provides the interstage cooling in this case. And BITZER does have requirements for the superheat that needs to be set at the motor barrel. And just to give you a rough idea, it's going to be approximately, say, 40° R is a reasonable number. You're sensing your superheat at the interstage mixing pipe where the refrigerant enters the motor barrel. This is another mode that you can operate the compressor with. And this is, again, as I mentioned before, this is basically the minimum that we can apply. The desuperheating only mode is the minimum. This gives you basic desuperheating of the interstage so that we don't overheat the compressor and burn up our oil, and to ensure we have enough cooling for the motor and what have you. It's the minimum. But of course, when we apply it this way, we can't take advantage of subcooling. But there may be other reasons to apply this. I've seen systems where both methods are used, but to be clear, if you're going to ever apply desuperheating mode and subcooling mode, please consult with us on this so we can work together on that. You have to be very careful. And just to be very clear, you never, ever want to use these two modes at the same time. Okay, it's one or the other, never both. Preferably pick one and go with it. But I've seen some sophisticated systems where it's just, you know, for whatever reason, the additional desuperheating mode was applied. You know, for example, for capacity control was one way of doing it. Some system design considerations, subcooler expansion valve. Now this is something generally you don't have to worry about because the subcooler expansion valve would be provided with the compressor. In the case of a new installation, you have the expansion valve, you have the filter dryer, and the sight glass and the solenoid valve are provided as part of the Interstage kit. And we just need to know about the application so that we can provide the right orifice. Because obviously if you have an orifice that's too large, then you're going to have a hard time controlling the superheat of that valve. So it's application specific, it's refrigerant specific, it's compressor size specific also. No traps in the liquid feed line to the Interstage mixing valve, or the Interstage TX valve rather. As I mentioned before, this provides Interstage cooling, which is critical. It's very important that it has the best quality liquid available in that system. So you always want to come off the bottom of the liquid line. And if you've got existing systems in the field where you find that the superheat is very hard to control, or it's high and then it's low, and I mean, you can evaluate valve size and things like that, but take a look at the way it's piped. And if you don't have a good quality liquid going into that valve, that creates some problems for sure. The evaporator expansion valve, electronic expansion valve or thermostat expansion valve, whatever is being used, it's very important to consider the liquid subcooling because when you have a situation where you're subcooling the refrigerant substantially like this, what it does is increases the size of your expansion valve. And if we're not careful, that valve, a lot of times you're kind of oversizing a valve anyways, because you pick the closest valve for the application. So you may end up with a valve that's, you know, 80% loaded when you design it anyways. But if you forgot to include the effect of the subcooling, the additional capacity that you get using subcooling, then it's very easy to oversize a valve. And as we know, oversized valves can lead to and will lead to hunting. Hunting leads to poor control of the evaporator and the possibility and likelihood of refrigerant, liquid refrigerant that is traveling down the suction line. And again, these are direct suction compressors. So the capacity, of course, of the main expansion valve needs to take into consideration the capacity of the evaporator, the operating conditions, but we never, ever want to forget that subcooling. The other thing is when designing systems that are going to use a two-stage compressor in a subcooling mode, it's very important that the manufacturer is aware of the subcooling. For example, you may buy a condenser unit from a manufacturer, and maybe you're buying some special type of coil that's got to be made up or something like that. Extremely important they know about the subcooling. The more subcooling you have, the less flash gases in the evaporator, okay, leaving the expansion valve, results in lower turbulence, which in turn leads to less heat exchange, which in turn could lead to laminar flow. And in this case, you're going to have a hard time getting the heat from the heat source into the refrigerant through the evaporator. So it's very important. Subcooling is always considered. In a situation where a suction accumulator may be used with a heat exchanger or boil out coil, as they're called sometimes, you want to do this after the brazed plate heat exchanger that's used for subcooling and interstage cooling. Because the idea is the subcooler, we want to load that up as much as possible, that valve. And what this does is it promotes as much flow as the interstage needs to keep that compressor down to BITZER's required superheat for the application. So generally, I wouldn't expect a suction accumulator with a boil out coil to do tons of work, but we want to take that off the table. Any additional heat that you add to the, any additional subcooling that you do to that refrigerant, you want to do it after the brazed plate heat exchanger. Okay, so let the interstage do its thing, and then you can provide that type of accumulator afterwards if you want. So your liquid loop in that heat exchanger essentially would be placed between the brazed plate heat exchanger outlet and the inlet to the expansion valve. This is a small table that I pulled from a Sporlan catalog at one point, and it shows you the effect of, if you take a look at the 100 degrees Fahrenheit column, you'll see that the safety factor, or sorry, the factor is 1, which means that the valves, the nominal size of the valve is whatever the tonnage rating is, multiply it by 1, that's what it is. But as the temperatures drop, for example, at 30 degrees Fahrenheit for, we'll just pick, say, R407C there at the bottom, not a common one actually for low temp, but I just put this here as an example. At 30 degrees Fahrenheit, we can see that the increase in capacity of that valve is 49%. So if you're already oversized by 20%, now you're going to be oversized by this much more capacity. And in the case of 422D, it's 70%. So I just put this up here just to show you the impact of subcooling. So we want to be very careful with that. Be careful with the suction line standard piping charts if that's what you're using, because most, if not all of these, are based on 100 degree Fahrenheit liquid. And again, if you're subcooling refrigerant, the capacity of each pound of refrigerant is totally different. And it really skews the numbers. So what can happen, just to keep this simple, is if you use standard charts based on 100 degree Fahrenheit liquid entering that expansion valve, you're probably going to end up with an oversized suction line as well. And we know what happens with oversized suction lines. Oil return is not very good. And this can create a lot of problems. When oil return is not good, and you've got compressors that are direct suction, and that oil is able to accumulate in the low side, and then maybe we go on defrost at some point in time, now all that oil is going to come back in a significant volume, and it's very dangerous for a compressor operation. Note that the interstage injection solenoid must be cycled with the compressor. So for example, one approach is using a normally open auxiliary contact. That's the simplest way. So if that compressor is running, you need to have interstage cooling. It should never be shut off during any mode of operation while that compressor is running. So this applies to economizing, desuperheating modes with or without pump down. The oil separator return. So this would be on a single compressor system. You would return this back to the motor barrel here. Oh, of course, I've got, sorry, I was trying to get back to here. It's actually trying to highlight there, but my controls seem to be a little bit different than what I'm used to here. Let's see if we can change the color here and make it red and highlight something. I'll just try that quickly, and if it doesn't work, then that will be okay. I'll give it a whirl. So somewhere back here, okay. The back end of the compressor on the motor barrel, basically there's a plug at, we'll call it the 7 o'clock position. If you're looking at the interstage or the motor, we'll call it the end bell at the back of the compressor, that would be where you return the oil. Of course, if it's a parallel compressor system, you're going to return this via an oil level regulator, which is installed at the sight glass position. There you go. there's the highlight. I forgot I had that there. So there's your oil return connection. So when sizing for your suction line and your expansion valve, we need to consider the capacity of 65.3. This is your evaporator capacity. Okay, and we've got 39.6 degree Fahrenheit liquid, and we're operating at -40 Fahrenheit saturated suction temperature, and we've got a saturated discharge temperature of 100 degrees. Orifice selection is quite simple. We need to know the compressor model number, of course. We need to know the refrigerant. Are we using a subcooler? In this case, yes, we're going to use a subcooler. We're going to, let's say we're using a 404 or 507, and the application is above a saturated suction temperature of minus 60 degrees C or minus 76 degrees Fahrenheit. In this case, we would use an 06 orifice. Okay, so it's that simple. And if you're not using the subcooler, that implies that you're using the compressor in a desuperheating only mode. In this case, you'd use the 03 orifice. There's also charts available for 407C, 407F, also available for 448, 449. For capacity control, you could alternate subcooling and desuperheating modes, but please consult us if you're ever considering doing something like this. You have to be very careful when you're switching modes. You can really create more harm than good in this particular case. And so please consult us if you're ever considering an application like this. But generally speaking, try and choose a mode and stick with that. Two-stage compressors, as with all compressors, are approved for use with a variable speed drive or variable frequency drive. We just have to be aware of the speed range. Generally speaking, it's 30 to 60 hertz for the two-stage series. In some cases, we can actually operate that compressor up to 70 hertz. But again, in this case, you would want to consult with one of us at BITZER so we can take a look at the application and see if this is achievable and safely for the compressor. Just when you're using drives, I know I've mentioned this before with VFDs. Anyone who's attended these other some of the other webinars where this has come up, generally you want to use a drive that has a good quality and exhibits low harmonics. Harmonics in the supply to a compressor terminals just always results in heat. So we can have multiple compressors and stage them, but we cannot apply any unloading, of course, because with the unloading, it's simply not available because we need all of the cylinders to accomplish both stages of compression. This slide just gives you an idea of approximately how much capacity drops when you shut the subcooler off and go to a desuperheating mode. So in the case of minus 40 Fahrenheit saturated suction temperature, it's 35%. At minus 80, on the other hand, it's close to 60%. Okay, but these are major changes in capacity, so you can't be just switching modes back and forth. And generally, we don't recommend it. It can be done, but as I said, it's best to consult with BITZER. Any compressor that requires auxiliary cooling, like head cooling fans, in this case, interstage cooling, in my opinion, it's always a good idea to have a discharge temperature sensor in there. It's really low cost insurance in the event that something goes wrong where we've lost our cooling, the ability to keep the compressor cool, or something's just gone awry and now our discharge temperature is just too high. We can install a discharge sensor and wire it basically in series with the motor PTC sensors. And then in the event of either a motor overheating situation or a high discharge temperature, the compressor will be taken offline safely. Just taking a quick look at parallel operation. I'm just going to flip through a couple of slides quickly here just for the sake of time. Single subcooler versus multiple subcoolers. Generally, it's recommended to go with single subcooler whenever possible when you're applying multiple compressors, because control can be very difficult. As your compressor staged down, you've got an oversized subcooler and you're trying to modulate that refrigerant and while maintaining good superheat. Can be tricky to do. So wherever possible, use one subcooler per compressor, and that's generally the most robust approach. And of course, the oil management system, it's going to be similar to any oil management system for single stage compressors with a slight difference, which I'll show you in a moment. This is a picture of a rack that was built in by BITZER Montreal several years ago. And this just shows that the paths through each subcooler, you can see that there's 1, 2, 3, 4 subcoolers here, one for each compressor. The idea is the liquid comes in from the receiver, takes a short path to the first subcooler, and then leaving the subcooler, it has this long path where it says cold liquid from subcoolers to get to the other end of the rack. The opposite subcooler, on the other end of the rack, you would pipe it so that the liquid from the receiver travels a long distance to get to that subcooler, and then a short distance leaving the subcooler. In general, what's happening there is we're just trying to equalize the flows. So unlike a single stage system, when you're using a low pressure oil management system on a two-stage parallel system, you want to make sure that you have your vent valve. In this case, it's an oil differential check valve, operates on a differential pressure, usually 20 psi or so. Or if it's a regulator that operates on a pressure difference, you want to make sure that you use your interstage as the reference pressure and not your suction header. Because remember, your crankcase is at interstage pressure. And if you're venting the oil reservoir down to suction pressure plus 20 psi, you'll never get any oil flow into the oil level regulators, because in fact, when the regulator is open, if anything, the oil is going to leave the compressor and go back towards the reservoir. And we certainly don't want to do that. When paralleling the compressors, we equalize them using another fitting that's in the back end of the motor housing. And in this case, we'll use a fairly large equalizing line, equalize that pipe down low between the compressors, and then that check valve from the low pressure reservoir then will be vented to this connection here. So, and we don't have a lot of time left, so just a few quick notes. When pulling down systems using two-stage compressors, note their maximum saturated suction temperature. So in this case, for 404, 507, and some other refrigerants, minus 13 Fahrenheit saturated suction temperature is the highest that suction should operate at. So if it's going to be higher because you need to pull that system down, it's very important, particularly if this is repetitive. So each run cycle requires this pull down. You're going to need to introduce, at the very least, maybe an electronic expansion valve with a programmed MOP or maximum operating pressure that can operate at, CPR or crankcase pressure regulator, something like that. If it's a storage warehouse that happens to be operating very low temp, in theory, you could just throttle the suction valves and until you get the plant down to temperature. And as long as you don't exceed the envelope, then you'll be okay. But what happens is when you're running high saturated suction temperatures, it's very hard on the high stage in particular. And I guess to some extent the low stage, because you're outside the envelope. But in the high stage, we have a very high mass flow rate. It's very hard on the reed valves. And you can see the scores on these tips here, the reed valve tips where they drop into the cylinder and sit against the suction rest every time the piston's traveling downwards. They can actually break off. Superheats, as always, are important. And yes, this is a two-stage compressor. As you take a look at that photo, our minimum crankcase temperature is 95, 100 degrees Fahrenheit or so. And in this case, you can see we're definitely not doing that. So in that case, so minimum superheats for your interstage are 20 degree Kelvin or 36 degree R. For most of the common refrigerants, with R22, which isn't really used anymore, but it was 30 K or 54 degree R. So, and I put some notes here. I'd be happy to share some of this material with you if you do send me an email afterwards, if you want to read up on it on your own, especially considering I'm kind of going through some of this material pretty quickly now. When you're checking your interstage superheat, you want to check the temperature at the point where the interstage enters the motor barrel, and you want to check the pressure at an MP port on a cylinder head. Now, generally, this would be on the high stage head. You'll see a port marked MP. Let's call it medium pressure. So on the low stage heads, you'll see LP and MP. On the high stage head, you'll see an MP and an HP. Okay, and there is something that we can check. There's some notes in here about if superheat won't come down. If it can't come down, you could be low on charge. Maybe the we have a flow issue on the interstage side, or there's a number of things that can happen. Valve starvation, the whole bit. Load is super high. But one thing I wanted to point out is when you are evaluating a two-stage compressor in the field, one neat thing you can do with a 6-cylinder compressor is you can take, again, this is the same formula I had shown you before, where you take the low stage, or sorry, the suction pressure and the discharge pressure, both in PSIA, multiply them together and take the square root of that number. And for 6-cylinder compressors, that should put you within about 5 PSI of what the software indicates. If your interstage pressure is riding kind of lower or closer to the suction pressure, that's an indication that you should probably open up that compressor, specifically on the low stage side. Take a look at the gaskets, take a look at the valve plates. You just may have a problem there. And on the other hand, if the interstage pressure is operating closer to the high stage pressure, that means your compression ratio on the high stage isn't quite as high as perhaps what it should be. So perhaps, again, we have a problem with gaskets where it's blown from the high side to the low side of the cylinders, or the valve plates have been damaged because there's too much interstage flow can cause that. So, and I'll skip this slide here. This is just on checking oil pressure. Always check between the, at the pump, negative and positive, or I guess you could check the crankcase versus the positive, but never check oil pressure based on suction pressure. Okay, and regarding controls, obviously we have to set the controls to protect the compressor, keep it in its envelope. But when you're connecting that low pressure control, I've seen this in the field where the low pressure control is actually connected to the interstage, and then we have a situation where the compressor never shuts off, even though there's no load on it. So you end up with a situation that looks like this, which is not very good for the compressor operation. Ports are indicated in the service manuals, the brochures. If you're not sure what a port is, you can look at the drawing. They're all marked, the ports, and then you'll have a legend that indicates what the various ports do. So I went a little over there, but that concludes the presentation. So we can leave this open for questions, Matt.
Excellent. Thank you so much, Phil. That was fantastic. We got a little cut off in the beginning of the recording. This is Phil Boudreau with BITZER, providing some fantastic insights. Now, I've got 4 questions for you if we want to do a kind of a lightning round. First one being from Dennis. Can you use R44-8A in 2-stage? And if so, is the operating envelope different than R44A?
Then R404.
Yeah,
yes,
R44.
you can.
Yep.
Yeah, you can use 448, and you can use, absolutely use 448 in a 2-stage compressor. Just keep in mind that the orifice size, oftentimes it is different than what we would use with 404. So if you're looking at a conversion, please contact us so we can make sure you have the correct orifice for the application. And the envelope is basically the same.
Thank you. From Trevor, is the bleed port in all BITZER compressors?
I'm sorry, I missed that.
Is the bleed port in all BITZER compressors?
The bleed port.
The bleed
okay, I'm
port.
not sure what the bleed port is. There's a vent, there's an equalizing line at the back of the compressor, and that's on all of the 2-stage.
Sure. Trevor, if you want to clarify in the chat there, we might have I just maybe misinterpreted that. From Dennis again, it was mentioned that you can operate at -90 Fahrenheit. Any concerns about running well below atmospheric pressure? Any concerns about system contamination if there is a leak in the low stage?
Yes, and you have to be very careful. Of course, anytime we operate in a vacuum, I mean, you never want to operate a motor in a vacuum. In this case, we're not, because the motor is in the interstage. So it's always going to be running above atmospheric pressure, quite a bit, in fact. But yes, if you have, the low side of the system, when you're operating in a vacuum, if that system is not really well sealed up, then you can run into some problems. If you start pulling in air and things like that, obviously you're contaminating the refrigerant. The air ends up in the high side of the system as a non-condensable, elevating pressures and things like that. So 2-stage compressors are great in that you can apply them for simply. It's a simple way to achieve low temperature refrigeration. There's other ways you can do this to keep the pressures above atmospheric pressure. Generally, you'll want to stick with like a cascade system or something like that. But absolutely, they're approved for use in a vacuum. They can be operated in a vacuum because it's just the low stage cylinders that are low pressure. But it is essential that your system is designed so it's sealed up nice and tight.
Thank you. Now Trevor clarified he meant the bleed port vent valve, which I believe you addressed.
Yes, it is, Trevor. Okay. All of these compressors have the vent valve between the motor section and the crankcase. Yes, that's true on all these 2-stage.
Fantastic. One final question, and if anyone else has questions, please get them now. And I'm just going to read the model number. Will DTS 347023-03 work in all BITZER compressors?
What was that number again? I'm not
sure. 347023-03.
Yes. Okay. So that is your discharge temperature sensor. And yes. And I recommend them. Actually, I recommend them on every two-stage compressor you put in. I recommend even on all single-stage compressors that require head cooling fans and things like that. Anything where application where the compressor requires auxiliary cooling, it's a nice way to ensure that your auxiliary cooling works. So I highly recommend it. Yes, it will fit on all the two-stage compressors.
Thanks. Those are great technical questions. Now you've got your contact information up on the screen. So if anyone has any follow-up questions, just reach out and you'll be there.
Absolutely.
Awesome. Super informative. Thank you so much. Oh, we got one more coming in from Justin. Is there anything else to worry about when using a screw in low temperature?
A screw compressor. Okay, so that's a different topic altogether. But however, screw compressors would require oil cooling when you get into low temperature applications. That's the main thing, because you're using oil to compress the refrigerant in those cases. So we want to make sure that our oil is not continually overheating. So you want to keep the oil temperature within operating instructions or the operating requirements that BITZER has in order to keep the discharge temperatures in check.
Thank you so much, Phil. We're at 101, so I think we'll stop it there. If you have any follow-up questions, reach out to Phil. And Phil, thank you so much for joining us today, making it work and all the fantastic information you shared.
Yeah, thank you very much for the opportunity. Take care.
Our pleasure.
Have a good day, everyone.
Likewise. And this will be available soon to share with your network if you want to use this video. Cheers.
Thank you, Matthew.